and then quiz on 11th November, time to be finalized, but most likely in the 8 to 9 slot in the morning. So, we are looking at the high Reynolds number limit which gives us the result that d omega dt is 0, where omega is vorticity. For uniform approach flow conditions, omega is 0 over the entire flow field. And we also have del dot u equal to 0. So, these two equations then become the governing equations for inviscid, irrotational, incompressible flow. Then we use the method of potentials u equal to gradient of phi, where phi is a scalar potential. Now, this will satisfy omega equal to 0 identically. And so, you can find phi from the mass balance equation. So, sometimes phi is called a harmonic potential because it satisfies Laplace equation. So, the outline for solving for a flow field would be solve del square phi equal to 0 for phi. Then get velocity as gradient of phi. So, we have u equal to phi x equal to psi y, v equal to phi y is minus psi x. So, remember that both phi and psi are valid potentials of the flow field. You could work with either phi or psi. I have just chosen to work with phi. It's also interesting to note that phi and psi satisfy what you know from your complex variable theory as the Cauchy-Riemann conditions. So that suggests that you could use complex variable theory for finding the flow field. So we will not pursue that direction as far as the present is concerned. We will examine if a given function is a valid potential. It is if it satisfies del square phi equal to 0. Now, what is the structure of that flow field? That can be examined by looking at the streamlines, and each streamline is psi equal to constant. Therefore, you have to find the stream function. So, if you know phi, then through the velocity field you can relate phi to psi as shown. Here I have used Cartesian coordinates. You have similar expressions in polar coordinates. Then once you have the velocity distribution, you can find pressure from Bernoulli's equation. Usually this constant is found from upstream conditions, which is symbolically written as p infinity over rho plus u square over 2. U is the approach velocity. Now, the big question we had addressed last time was how good is the solution? In other words, does it match experiments? So, one example was flow over a flat plate. For which phi is equal to ux, and then you can apply the connection between phi and psi and get psi equal to uy. Now, there will be a constant of integration. So, you can set psi equal to 0 wherever you want as per convenience. So, we had set psi equal to 0 on y equal to 0, giving the constant to be 0. So, it represents, this is flow, is uniform flow approaching a flat plate, and it goes past this plate undisturbed, because all the streamlines are psi equal to constant will mean y equal to constant, which are lines parallel to the x axis. So, the flow goes past this plate undisturbed, giving rise to, so this is a plate. So, this u velocity, u vector is also capital U square. So, p is equal to p infinity. The pressure distribution over the solid surface. So, specifically you can write it as p x y equal to 0. Y equal to 0 is the flat plate, and as a function of x is just a constant. Does it match experiments? Of course, you have to do experiments at the limit of high Reynolds numbers. Okay. So, these are typically wind tunnel experiments. Why wind tunnel? Because you can generate high velocities, you can place large objects in it, and viscosity of air is very small. together it will give you a small, it will give you a high Reynolds number. So, these are so if you measure the pressure distribution along the surface, it turns out that you will get P equal to constant. So, matches experiments. The second example that we considered was flow past a circular cylinder of radius capital R, upstream velocity is capital U, this is x, y, r theta. The velocity potential was shown to be u times r plus capital R square over r cos theta, from which you could find the of course, you could find the stream function. You could also find the velocity distribution. The shape of the object was obtained by noting that u r is the partial derivative of phi with r, which is u 1 minus r square over r square cos theta, and on r equal to capital R, u r is 0. So, suggesting that r equal to capital R, that is this circle which is flow past a cylinder. Why flow past a cylinder? Because when you take the limit of r approaching this, if r approaches infinity, u r is equal to u cos theta, and similarly you can show u theta is minus u sin theta. That means it is this uniform flow in the far field, and in the near field it is flow past a circular cylinder. So, similarly you can show u theta is equal to 1 over capital 1 over r, the derivative of phi with theta, is equal to u 1 plus r square over r capital R square over small r square, cos theta becomes sin theta, all with a negative sign. So, on r equal to capital R, u theta is equal to minus 2 u sin theta. So, P we get the pressure distribution on the cylinder by applying Bernoulli's equation. So, this was written in compact form as P over the surface of the cylinder divided by half rho u square is equal to 1 minus 4 sin square theta. So, when theta is 0, that is this downstream point, u r is of course 0, but u theta is also 0. So, you have stagnation points A and B are stagnation points where UR and U theta are both 0, and this is the expression for pressure distribution. Now, you can integrate pressure on the surface of the cylinder and get the forces acting on it in the x and the y directions. These turn out to be 0. We are talking about high Reynolds numbers, which is certainly an incorrect result. So, but for flow over a flat plate, it seemed to be correct. Now, let us look at another example. Where we have added this extra term, and then we showed that this will represent uniform flow approaching a circular cylinder, where the cylinder is given angular rotation and the angular velocity is connected to the parameter gamma. So, if you are given the angular velocity, you can find gamma. So, here, so I will now write down the final result. The pressure distribution is given by 1 minus 2 sin theta plus gamma over 2 pi u r, where gamma is 2 pi r square omega. This is the pressure variation over the circular cylinder, and if you carry out using the same formulas we wrote last time, x continues to be 0, but y is rho u gamma. Okay. So, let us write down on the cylinder. So, now the lift is no longer, y is the force acting in the y direction, capital Y is the force acting in the y direction, which is at right angles to the flow direction. Therefore, capital Y is also lift experienced by the cylinder. So, does this result, it is a non-zero value, does it match experiments? To a great extent, yes. So, this result and this was independently discovered by various engineers. So, So, traditional books on fluid mechanics will call it Magnus effect. If you read books on aerodynamics, they will call it the Kutta-Joukowsky law or theorem. But for our discussion, we will just call it Magnus effect. X equal to 0, y is rho u gamma. So, the natural question to ask is, why is potential theory incorrect in the prediction of drag, which is x equal to 0? So, that result came from pressure. What about shear stresses? You have an object and you know it will experience shear stresses and normal stresses. Normal stresses on the surface will become pressure, and shear stresses for potential theory, it is 0 because viscosity is 0. So, let us examine pressure distribution. Let us start with a circular cylinder. We had that result that P r theta minus P infinity over half rho u square is equal to 1 minus 4 sine square theta. If you plot this variation, so theta is measured from the positive x axis, but flow is from the left. So, this is just let us call it conventional to plot pressure variation from A to B. Okay, so, point A will be theta equal to pi. So, we normally plot pressure as a function of pi minus theta. So, that point A is here, point B is here. At A, theta is pi, so it is just 1. So, here plus 1, and at a point like C, where theta is pi over 2, it is minus 3. So, C is somewhere here. So, this is what is Cp? Cp we called it pressure coefficient, just continuing with the notation of Cl, Cd and now Cp, that dimensionless quantity. This is the pressure variation over the surface of the cylinder. This is the result that gave us 0 drag. So, clearly if you do an experiment and measure pressure, this is ACB, you will have C prime. So, it is symmetric, both C and C prime pressures are equal, which is why the lift is also 0. There is symmetry with respect to the y axis. The pressure variation on the left is the same as the pressure variation on the right. Same thing above and below. So, I think sometimes that pressure variations at point A, this is point B, this is point C, it is plus 1. So, it is a maximum at A and B, and it becomes negative, but let me show that negative quantity as like this. Okay, so pressure progressively decreases from A to C, right? From this is A, from this is 1, and here it is minus 3. It progressively decreases. What is the flow direction? This is the flow direction. Okay, and then from this is point C. From C to B, pressure increases and recovers its original value, which is this value. And you get the same variation below. So, there is left-right symmetry and top-bottom symmetry, which is why the forces are adding up to be 0. Okay. Now, this result of course is incorrect, and if you carry out an experiment, you get a very remarkable result, which is the basis of a lot of fluid mechanics. That remarkable result is from A to C, the experimental data matches potential theory in the region A to C. That match is pretty good. Now, in terms of pressure variation, you recall A to C is a region of favorable pressure gradient, because pressure decreases in the direction of flow, along the flow direction, local flow direction. Flow is, if you look at the streamlines, flow is going around the cylinder. You have seen plenty of videos. Flow will go around the cylinder. So, this AC is a region of favorable pressure gradient, and CB, where pressure increases in the direction of flow, right, like this, from minus 3 to 1. Is called the region of adverse pressure gradient. So, in the region of adverse pressure gradient, the match between experiment and theory is quite poor. Okay. So, the difference between theory and experiment is seen in this part CB, which is the origin of the incorrect result. The drag acting on the cylinder is 0. So, I should say this gola, this circle is experiment. Let me just to emphasize the difference between theory and experiment. The circle, open circle, is experiment for the favorable pressure gradient part. So, let us use a cross for the portion CB. So, it is not a simple departure, it is a major departure, but it turns out that it's not that pressure decreases and then from point C it should increase as per potential theory. It should increase and recover its original value. Instead, it just remains constant. Okay. Those crosses show that Cp, that is experimental data, remains practically constant. So, now you can try substituting the experimental pressure variation in the formula for drag. What is that formula for drag? Here we had it here. In this formula for drag, this is the formula for drag, minus p r theta cos theta. So, instead of putting the potential pressure variation here, you may want to put the potential variation in the favorable pressure gradient region and constant in the adverse pressure gradient region. So, redefine p r theta as potential over AC. What is AC? Favorable pressure gradient. And p r theta equal to constant over Cb. This is adverse pressure gradient. Okay. So, favorable pressure gradient would be pi minus theta over 0 to pi over 2, and adverse pressure gradient is pi over theta equal to pi over 2 to pi. Okay. So, now you can split the integral. You can just do calculations for 1/2 of the cylinder, double that is for the full cylinder. So, instead of 0 to pi, you break it up into 0 to pi over 2 and then pi over 2 to pi, and apply potential theory over favorable pressure gradient. So, I will let you do the calculation, and then that gives you okay. So, that will give you a non-zero value of the drag coefficient. You remember this? Some variation like this. This is the experimental variation. The initial part matches the Stokes flow approximation. For large Reynolds number, you see that CD is nearly independent of Reynolds number, and this value is about 1.4. I am talking about a cylinder problem. Now, there is a dip here later on that we will study separately. If you adopt this approach, that this is if you work with this pressure variation, that it is potential up to pi over 2 and constant later, how will the pressure distribution look on the cylinder? But over this part, it is a constant. So, you can see that it is potential. So, now the left right symmetry is broken, and you expect a finite force acting on the cylinder. So if you look at the expression, it will be independent of Reynolds number. So let's look at this expression. Look at this expression for x. If you scale it by half rho u square, then this pressure does not have Reynolds number in it. The Bernoulli's equation has no Reynolds number in it. So you will get a number out of it. So you will get some data like this. Slightly higher than 1.4. I think I don't remember, some 2.5 or something. So, but potential theory gives you 0, which is absurd. But if you make this correction, you get a result that is sort of similar to the experimental value, not very close to it. The reason it's not very close to it is this variation here is not strictly constant. This part so we have approximated this part, the adverse pressure gradient, as strictly constant. It's not strictly constant. But if you do that, you get a result much closer to experiments. This is with the revised pressure variation. So, this observation, is it universally valid, that in favorable pressure gradient? So, comparison with experiments tells us that when the field is has a favorable pressure gradient, potential theory will hold. Can we test it in any other geometry? For a flat plate, pressure gradient is 0. There is no variation in pressure. You remember the nozzle geometry. So if you apply Bernoulli's equation, velocity will be increasing in the x direction. So from Bernoulli's equation, pressure will decrease in the flow direction. So it's a favorable pressure gradient problem. You can carry out pressure measurements, and indeed you will see that experiments match potential theory. So you can write down good match with experiments. Now, can you give an example of adverse pressure gradient? Adverse pressure gradient, the opposite of a nozzle, a diffuser where velocity decreases in the flow direction. So, when you put that in the Bernoulli's equation, you will get pressure increasing in the flow direction. So, the opposite of a nozzle is a diffuser. Usually, what is the cross section of a nozzle or a diffuser? I am not showing it. What is the cross section? Circle, right? Circular cross section. So it's like a conical. That would be a conical diffuser. You can also have a rectangular diffuser, square diffuser. Conical is common. Similarly, you can have a conical nozzle also. with circular cross section. So, potential theory will predict some increase in pressure. This is potential theory in the x direction. I should say potential theory. But experiments show that pressure will not, this is called pressure recovery. It will not recover, it will not increase along this line. Instead, it tends to become a constant. So, these are so the general observation that we summarized in this slide, if it is favorable pressure gradient, pressure variation at high Reynolds number will be potential. If it is adverse pressure gradient, it will turn out to be nearly constant, okay, like this part. It will turn out to be nearly constant. That increase in pressure in the flow direction will not be realized in an experiment. So, as a net result, you have this circular cylinder, you have greater force acting on it on the left compared to the right, and this object will experience a force to the right, which is what we call drag. So, if you look at circular cylinder with circulation. Circulation strength is gamma. So, the velocity components plus gamma over how much was it? Minus 2u sin theta minus gamma over 2 pi r. So, if you have to plot the flow patterns, one approach is, of course, you can look at the streamlines and plot constant psi values. The other approach is to look for stagnation points. For gamma equal to 0, those are points A and B, and the flow splits equally above and below the cylinder. So, the stagnation points with circulation are so setting u theta, u r anyway is 0. So, u theta, you set u theta equal to 0, you will get an expression for the angle sin theta as minus gamma over 4 pi u r. Of course, you have to ensure that the right side should be less than 1. Okay, so this will give you, so sin theta is negative because all quantities on the right hand side are positive, gamma is positive, u, r, they are all positive. So sin theta is a negative quantity, so the points A and B now, they shift to the third and the fourth quadrants. So these are points A and B now. Okay, so the streamlines trying to show that the symmetry with respect to the x-axis, above the cylinder and below the cylinder, there is a distinct difference which gives rise to lift acting on the object. Okay. In the presence of an adverse pressure gradient, you have left-right break of symmetry giving rise to drag. So here also you can locate points of adverse pressure gradient and then set pressure equal to constant. So movement of stagnation points breaks symmetry and generates forces. Okay, so I think in the tutorial of Thursday, you have several questions related to potential theory. One of them says, I have a circular cylinder rotating at some angular speed, maybe 100 RPM, and then it is placed in an air stream with a velocity of 1 meter per second. What will be the lift generated by this arrangement? How much is the lift? It's just rho u gamma, except that you have to relate, u is 1 meter per second, relate gamma to omega. Okay. Okay, so I want to stop now and see if you have any questions. On Wednesday, we'll take the story forward and ask, why does pressure variation depart from theory in the region of adverse pressure gradient? What is so special about the adverse pressure gradient? Okay, that discussion we will take up on Wednesday. But now we have a good, 2 minutes time. If you have any questions, you can ask me. Yeah. If your hand goes up, you must ask. Your hand also, I'm just trying to track people whose hands are going up. Yeah. Are you back in reckoning, which means are you back in touch with the course? Or it will require you some time? So you will notice that half the lecture was a repeat of what we have done in the past 2 weeks. If you have a clear question, you can stand up and ask, so everybody can hear. How many of you know how to solve Laplace equation? You know how to solve Laplace equation. What is the method that you are familiar with? Separation of variables. Are we using separation of variables? Those solutions given, I gave you phi equal to something, but that did not have an infinite series. So that solution was not obtained by separation of variables. It's obtained by some other method. So next time I'll briefly comment on how the solutions are obtained and then connect them with your tutorial problems on Rankine half body and full body. Have you opened the assignment? You have opened, you see this phrase Rankine full body, Rankine half body. Okay, so I see you on Wednesday.